Let us talk about microprogrammed control unit. So generally in microprogrammed control unit, we will be writing some code, I can say. Okay, it's not a circuit. So I can say that we will be storing the control signals in a memory. Remember it. It's all about control signals. Finally, you remember one thing. Control unit should generate control signals for for making your circuits work, right? Control signals. That control signals can be generated using circuit that is nothing but hardwired, right? If you use circuit, then it is called hardwired control signals. Second one, we have microprogrammed control signals. We can program them. Sir, why we have to program? For what kind of instructions we have to do microprogrammed control unit? We will see. Especially for RISC kind of architectures, people prefer hardwired control unit because it is simple to design. But when the instructions are CISC instructions, then the number of control signals, otherwise the complexity will be increased. That's why generally we don't design hardwired control unit. Rather than that, we go for microprogrammed control unit. In that, we will be storing the control signals in a memory. That is the idea. Now we'll see how that idea will work. So especially in CISC kind of instruction sets, the number of operations are highly variable. We can't divide the work into 5 parts. So some instructions might take 5 units, some instructions might take 10 units, some instructions might take 7 units. Example, see this instruction, a simple instruction, add R1, R2, R3. So it is a RISC kind of instruction, right? So that's why it takes only 5 stages. Correct? We can design a 5-stage system. But when you have this kind of instruction, add memory of 100, memory of 200, imagine this kind of instruction, memory of 300. Really this, what is the meaning of this instruction is easily we can predict. Go to memory of 200, okay. Go to memory of 300 and fetch the operands, right? X, let's say Y. Then add them, okay. We need adder circuit, X plus Y. Then store it in memory of 100. How complex this instruction is. To execute it, you need lot of cycles, correct? So this kind of instructions are generally called CISC instructions. Then you might require more than 5 stages to execute this instruction, correct? Now that's why for this kind of model generally people use, it will be very difficult because that is what experience says. So according to experience, people realize that. So for this kind of CISC kind of instructions, microprogrammed control unit will be better, where we will be storing the control signals using the memory. That means we are programming the control signals. We are not creating the circuit for the signals. Okay, there are 2 models. Let me repeat again. We can generate control signals using circuit, that already we covered. Second thing is program it. So there will be a program which is going to generate the signals, okay, through the memory. That's why we are going to store the program in the memory. We will see that detail slowly. Now example, let's say you have now, from now onwards we don't assume any particular instruction because we are now going to talk about CISC kind of instructions. That's why, so for CISC kind of instructions, so what typical instruction might be like this: add, again I'm taking this one, add maybe R1, memory of 100 and memory of 200. First of all, we have to fetch this instruction, correct? After that we have to decode it, right? Then after that, remaining stuff, again we have to go for memory access. Again we have to go for memory access. I can say that go for memory access, again go for memory access second time, right? Then after that do addition, right? Then after that storing. So here you can see 1 2 3 4 5 6 steps we can see, correct? Now what I want to tell you is, but fetch and decode are common. Every instruction should be fetched, every instruction should be decoded. That's why what I can say is the code for fetching and decoding might be same, right? Now assume that, let's say this instruction's fetching is like this, okay, like a RISC instruction fetch. What are the things we have to do to fetch an instruction? First of all, program counter data, whatever the address, we have to take into M address. That means we have to take in some register, which is nothing but typically memory address register. Okay, after that we have to read the memory. that memory interface will work with this memory address register. Whatever the address you show in memory address register, that will be taken by that memory interface, and it will read the memory if you issue this operation, right? After that, we have to wait for this signal. Did you remember? Already I told you, if the data is not available in cache, we have to go for main memory. That's why it might take some time. So that's why we have to wait for this signal. After that, we have to, when we get this signal, then data is available, that will be transferred to instruction register. After that, program counter should be incremented. So here I would like to tell you one thing. All these things are called, micro operations. I can say this entire thing is one micro operation. Okay, one or more micro operations. Don't worry about it. To execute one instruction, we need some atomic steps, right? Like, one step, one step, one step, in that way. All these things are called micro operations. Okay, that is enough for you. So don't go into details of micro operations. So these micro operations all together will form one instruction. Okay. Now for any instruction, the set of micro operations are same. Correct? Because fetch is same. Understand? Similarly, for any instruction, typically maybe decoding is same, but the remaining parts will vary. It depends on the instruction. For add it will be different, for load it will be different, for store it will be different. Correct? So that's why what we are going to do is, example, let's say just focus on any instructions fetch. To do this fetch of the instruction, probably you will be doing some micro operations. To do all these micro operations, we need to enable some signals, correct? Control signals. So assume that, let's say, the control signals required to do all these operations are C1, C2, C3, just for assumption. So in micro programmed control unit, what we are going to do is, we say like this: to perform fetch operation, which is one micro operation, I can say. Okay, so to fetch micro operation, we require, how many control signals we have to generate? C1, C2, C3. From now onwards, we are not going to particular details, like, so really how many control signals are required. Don't count and tell me, sir, here we require 5 control signals, because already I have seen circuit. In that circuit we require 5 control signals. Forget about that. We are talking in an abstract way. That means, we are not talking about a particular machine now. So because already you know the concept, right? Just try to interpret it in a high level. That's why don't go into particular details. Example, to perform fetch operation of any instruction, whenever I say that you require only 3 control signals, simply believe it. Okay, assume that such circuit exists. So assume that, let's say, there are only 10 control signals. Okay, again it's an assumption. I am working on one hypothetical machine which has only, otherwise let's take 64 control signals. Okay, C1, C2, C3, so on, C64. So there are only 64 control signals you might require at any time, but not all at a time. Some of them, correct? Especially for fetch operation, out of that 64, we require C1, C2, C3. Sir, I am not understanding what is control signal. Then recall. In the RISC architecture, I mean, already we have seen one particular machine, right? In that PC enable, PC select, right? Multiplexer selection, all that are control signals. So here for fetch, I am assuming that you require 3 control signals. Let us say C1, C2, C3 out of 64. Then what we are going to do is, we are going to program it. That means in the memory. Don't ask me where are you storing this, this storage. Somewhere. Forget, assume that it's a memory. Maybe it's not main memory. Generally it will be stored in random, read only memory, ROM. Okay. So we will see that detail later. At this moment, some memory. In the memory, so somewhere I am taking one row. In that row, I will be writing like this. I will be writing a 64-bit information. So first bit indicates about C1. Since C1 signal is compulsory for fetch, I write like this: 1, C2 1, C3 1, all that 64 other signals should be off. This is called micro instruction. So whenever this micro instruction is executed, that means whenever I take this and I execute it, that means the appropriate signal should be generated. Executing this micro instruction means this is one micro instruction. Okay, if you execute it, then because of these 3 bits once, C1, C2, C3 should be generated. Such a way, again you have to design a circuit, a little bit circuit. Okay, not a big deal. Now second thing, After fetch we have to do decode, right? Assume that for decoding some 7 signals are required. They are C3 to C9. Okay. Then what is the micro instruction for that decoding? For decoding, micro instruction will be like this. I am writing here. C0, C1 0, C2 0, C3 yes, C4 yes, C5, C6, C7, C8, C9 followed by all the remaining bit zeros. In that way we have to generate 64-bit micro instruction. Now after fetching and after decoding, some more steps are required to execute one particular instruction. Let us say that some other parts of the execution is like this. We need fetch and decode. Now example, let's say you want to execute add instruction here, which I have shown, right? Example, this one, add R1 memory of 100 memory of 200. To do that, what extra you need is whatever it is. Let us say, so for that you require some control signals, correct, and some operations, and 5 more operations. Let's say you require 5 more micro instructions, let us say. Okay, 5 more micro instructions. So let us say that micro instructions are 1, 2, 3, 4, 5. Okay. Now, sir, who is going to do all this stuff? We will be doing. If you are a designer of this architecture, then by after understanding this instructions model and after understanding your machinery, you know your machinery, right? Your circuit, and you know your instruction execution model. So simply understand your circuit and understand your instruction model. Based on that, just now I see how you have created a micro instruction for fetch and decode. In the same way for all other 5 more micro instructions. Okay, so which are part of execution of your total add instruction, we have to write a code. Okay, so that is enough. We are not seeing the complete details, like how to write exact code doesn't matter for us, and especially for gate you don't really require. Okay, it depends on the architecture and everything. So we are understanding in again high level. So that's why finally this micro instruction, and these 5 micro instructions, if you executing micro instruction is very simple. Take that word that is called control word, and based on the positions of ones you generate appropriate signals. Finally, end of the day, what are we doing? We are generating the control signals. What is the difference between hardwired and this one? In the hardwired, the circuit was automatically generating the signals. Such a way we created a complex circuit, but here we are programming it, right? So in that way, these are all instructions in the program. Now I can say that here what finally we realized is, you have micro instructions, correct? To execute any instruction you require some set of micro instructions. Especially for add, I said you need 7. It may be true, may not be true. Just for understanding purpose I am assuming 7. Maybe some, it depends on the exact implementation. Second one, the set of micro instructions, if you gather, okay, like this 1, 2, 3, 4, 5, 6, 7, which forms all the control signals required to execute one instruction, that is called micro program, okay, or micro routine. So this is the micro routine for add instruction. Similarly, there will be a micro routine for load instruction. Similarly, store instruction, correct? So finally what I want to say is, so every instruction, to execute it we need one micro program, correct? Now the important thing which we have to talk about is, what is the structure of this micro instruction? That means if you have micro instruction, is it sufficient or anything else? We will see that details. So let me elaborate these details. So finally, fetch routine and decode routine. That means, let me use routine word here. So fetch and decode routines are required for every instruction. Now we can feel like this. So maybe for add instruction, this is the micro routine, and maybe for, I can say, store instruction, that means remaining part of store instruction, this is the routine. In that way, for load instruction, maybe this is the routine. In that way you can imagine. Okay. Now, sir, what is this control address register, sir? I will tell you. What is this micro program? What is this micro program counter? I will tell you. First of all, you should understand one thing. Whenever you have an instruction, the instruction execution should start with fetch, right? That's why automatically control should go to the starting address of the fetch routine, correct? Assume that, let's say, fetch is located in this memory at 100. Then initially your micro program counter should show 100. Now, example, let's say your instruction is add. For executing add instruction, what should happen? Fetch should be executed. For that, appropriate control signal should be generated. For that, this micro instruction should be executed. After that, this micro instruction, which is related to decode. Later, the control should come to, let's say, add starts at 200. Then automatically micro program this counter should show 200. For that, what we have to do? What is the logic? So how to plan so that micro program counter shows exactly the address of the micro instruction which we want to execute, right? It depends on the instruction. If the instruction is store, what should happen is, example, let's say stores remaining in routine starts at 300. What should happen, So in store also, first of all, we have to fetch the instruction. That's why the appropriate control signals are these signals. After that, decode instruction should be generated. After that, we have to generate instructions or control signals related to store instruction, correct? So can I say one thing? Automatically control should come to the first micro instruction related to store part. So that is the way it should happen, right? Assume that, let's say, these 4 micro instructions are related to this store instructions, micro instructions. So that whenever this micro word or micro instruction, this micro instruction, this and this, if these micro instructions are executed, executing them is nothing but taking that micro instruction and generating the appropriate signals. Finally, already I told you one thing. End of the day, executing our instruction is nothing but generating appropriate control signals. That is what we want. But we are doing with that program. For that, see, some of the control signals which are common for every instruction are here, and the remaining signals which are special to a particular instruction are stored as a program for every instruction, correct? So that's why I can say that this area is micro program related to add instruction, and this is micro program related to store instruction, so on. In that way, for every instruction there should be one micro program, correct? Apart from that, what you want? Sir, why this control address register you did not tell us? I will tell you. So what happens is, this micro program counter, of course it is not required, but if we have this, so how we are going to use it, I will tell you. Initially, let's say you are in the early morning, what happens? Your micro program counter can be loaded with 100, so that we can start doing we can start generating the control signals related to fetch instruction. For that, what we do is, initially always whatever we have in micro program counter, we keep that in control address register. We can use this control address register to index this memory. If control address register shows 100, then we will be indexing the memory location at 100. If this control address register shows 200, then we will be indexing 200. In that way, control address register can be used to access the memory. Now, why this micro program counter? This micro program counter always, is going to, this we can use for sequencing. Okay, so here, I mean, we are using 2 registers, but with 1 also we can do, but I am just showing with 2. Okay, doesn't matter. So this is for sequencing. So every time, example, let's say 100, I will tell you one possibility. Just focus on add instruction. So for add instruction, the instruction to be executed is, micro instructions to be executed is 100, 101. After that, control should come to 200, then 201, 202, 203, let's say 204. That is what my assumption. These are the micro instructions related to your add instruction. For that, your program counter should go like this: 100, then 101, then 200, then 201, then 202, then 203, then 204. Here I am assuming that this memory is word addressable. That means for every different word I am giving one number. So this is the way my program counter or micro program counter should be sequenced. Okay. So we use micro program counter to show the order of the sequence of execution of the program, micro program. and always control address register we use to index, that means to identify the right memory location to fetch the instruction. Okay, in that way, so this register is separate, this address register can be separate. Okay, in that way we can plan. Just remember that. Now the question is, sir, how you change your micro program counter appropriately so that after 101 will jump to 200? Sir, how do you know that we have to jump from 101 to 200? And sir, if the store instruction, you have to jump from 100, then 101, then 300, not 200, correct? But how do you plan it? Further, in this model, how they planned is, they have, focus on this instruction. The next instruction is generally stored in micro word. Let us use a word called micro word. All these are all words. So each word, because we are storing here all the words, these words are nothing but micro instructions, right? That's why let us use a word called micro word. So each micro word or micro instruction contains two things, I can say. So conditions appropriate for doing some operations. Second one, next address, correct? Since next address is not always immediate one, sometimes it is jump, there is a jump, that's why one more field is required in the word, that is next address. Okay, now from now onwards that will be the usage. Second one, sir, what is this control data register? I'll explain. So whenever you specify any address in control address register, so this memory can be designed such a way that whenever some address is specified, automatically the appropriate data will be selected and that will be automatically transferred to this control data register. So this control data register is used to hold instruction, okay, which currently you are processing. Understand? So example, let's say at this moment initially micro program counter is 100. Then when you want to execute the micro instructions, so 100 will be first of all transferred like this. Okay, such a way we have to plan the circuit. There should be extra circuit that should do it. So 100 should be moved here. Then immediately because of that, this micro word will be fetched. Correct? Now already I told you, whenever you specify 100 here, we have to design our circuit such a way that automatically this memory, whatever the word we have, it should be transferred here. Okay, let us transfer here 1 1 1 0 0 0 0 0 0 something up to 64 bits. Then it is remaining field is next address. Okay, so here we write the next address. Maybe you can write next address 101. So that what is going to happen is, first of all, there will be some extra circuit. We will see the details later. So because of this pattern, appropriate control signals like C1, C2, C3 will be generated. Such a way we have to plan. Okay. Now C4 to C64 should not be generated. That means their bit should be 0. Now the next address 101. That means this should be copied to microprogram counter. Now in the next cycle, what happens? Control address register gets 101, and because of that we fetch what? This instruction. Then again that will be transferred to control data register, and again this part will go to control signals. That means, so appropriate control signals will be generated using the micro instruction, otherwise this control word, and this next address we will be using for the next instruction. Might be you have to write like this. After 101, where we have to go? We have to go, depends on the instruction, correct? Maybe for add instruction or maybe load instruction, we don't know, right, where to come. So you tell me, after executing this fetch and decode, how you decide whether it is next is add instruction or store or load, correct? So that's why what I want to tell you is, we have to take the input from your opcode of the original instruction. That's why, so let me show here. This is your program counter, micro program counter. So first of all, I show complete idea. Example, let's say your instruction is add. Then first we have to fetch it. That's why micro program counter initially should show 100. So recall, executing add instruction is nothing but doing a stage called fetch stage. After that decode. After that remaining instructions are micro operations. They are nothing but add routine, correct? So finally we have to generate signals for fetching. signals related to decode, signals related to add routine, correct? So what I want to tell you is, for that if you observe the machine in this memory addresses, so your microprogram counter should start at 100, then 101. That's not a big deal for us because we can store 100 here, 101 here. After that we can write next address, correct? But after 101 we should go where we have to go for 200. But how you decide? That's why your microprogram counter is generally also connected to one more thing. That means your microprogram counter should take input from two things. One is from here, that means next instruction, next address. Second one from the opcode of your instruction. So where is your instruction? Recall, it is in instruction register, right? So in the instruction register there will be opcode part, right? So using that opcode we have to somehow decide that the next instruction is 200. Okay, so what we have to plan is, so by seeing the opcode of the instruction, somehow you should be able to differentiate what is the starting address of the original routine. Example, let's say it is store. Where store is starting? 300. We have to plan a circuit such a way that if this opcode is opcode for store, then automatically microprogram counter should be filled with 300 so that we can come here. In that way we have to plan. So yes, it's not a big deal, correct? So for that we should have a decoder. That decoder should take opcode as input and it should generate memory addresses properly. If the opcode is add, it should generate address 200. If opcode is store, then it should generate 300. In that way one circuit we have to plan, so that what happens, then your microprogram counter will be properly sequenced, correct? That is what our goal. Now so slowly you realize that your microprogram words, if you see micro instructions, what should be the structure of your micro instruction? Micro instruction should contain at least two parts. One is for generating the control signals, correct? So this part is going to generate the control signals. Second part is sometimes showing next instruction. Okay, so that is about this microprogram instructions. Now we'll see more details about this microprogram control unit. So for that there are two things actually: vertical microprogram control unit, second one horizontal. So what is the difference between horizontal microprogram and vertical microprogram, we will see. Okay.